Welcome. Today we will look at a very interesting equipment that is commonly used in microfabrication sensor testing laboratories. This is called the Micromanipulator system, which you can see here. The system is kept here. First I will go through what is a micromanipulator, what is the concept of it, and why it is required for a microfabrication course or a field, a lab which works in the microfabrication field. And then we will go into the details of this particular equipment, what are the different components in it, how you can use it, and finally we will end it maybe in this module or in another separate module. We will end it with a small experiment where we will use this on a sensor to see the response. So, getting started, what is a micromanipulator? As the name implies, this equipment is used for making micro level or micro scale manipulations or movements in your experimental setup. So, this equipment per se will not go into any product that you make, but it forms a very integral and important part of your testing setup. That is the process by which you characterize your sensors. For that process, a micromanipulator system is unavoidable and very important. So, as I have told now, what is a micromanipulator? A micromanipulator is used for making micro scale or micro level manipulations or movements with respect to your sensor characterization. So, let us say we have a pressure sensor. Let us say assume that this surface of my hand is a pressure sensor, and what does a pressure sensor do? It senses pressure applied on its sensing area. Suppose this is a sensor and we have a sensing area here in this in the palm of my hand. Let us say we have a sensing area, and I assume that my fingers are the sensing contacts. You might have already seen several sensors that Professor Hardik had shown you in the courses. So, let us say assume that these are the contact points and this is the sensing area. Now, this sensor, what does it do? As the name implies, it does pressure sensing. For that, what we have, let us say we are measuring the stiffness properties of biological tissues. Then what do? We take the tissue which will be around 10 mm or 1 centimeter in height and 1 mm in diameter. It will be a cylindrical block. Let us say we keep that on top of this. So, for the time being, let me say that this is the tissue. I have just put a nut here. I think you can see the nut. So, this is the tissue. Now, you have kept the tissue on top of the sensor, and now you want to see what is the stiffness of this tissue. For this, what you have to do, the stiffness of the tissue is contained in the tissue itself, not on the sensor, correct. So, what the sensor does? The sensor picks up the pressure applied on it. When we place the tissue by default here, there will be a base pressure that is applied. So, that base pressure we can measure from these contact points. This pressure will get translated as electrical signals and we will tap it from here. Now, we want to measure what is the stiffness of the tissue. What do? Let us say this is something called an indenter. So, this is a 3D printed indenter. This is a macro scale, it is not that micro level, but it is for understanding purposes. This is a 3D printed indenter. What does an indenter do? It indents or pokes or manipulates on the surface of the sample. So, let us say we have brought this indenter, and for the time being, for characterizing the sensor, we are putting the indenter and pressing the tissue with the indenter. So, when we press, this indenter will apply one force on the tissue. The tissue, because of its elasticity and stiffness properties, will translate a different pressure at the bottom of the tissue or on the surface of the pressure sensor. So, we press it, and then this tissue, because of its elasticity, translates a different pressure on the surface of the sensor. This way, whatever information gets measured from these contact points as the pressure being measured will inherently have the information of the stiffness of the tissue in the measured value. Now, so this is generally how we are measuring stiffness properties using a pressure sensor. You can use other sensors also to measure stiffness properties, but for your understanding purposes I am taking this very simple example. So, now we have seen that we have the pressure sensing layer, the contact points, the tissue, and we have the indenter. Now, I think the limitation is becoming slowly clear to you. When we are doing this with our bare hands, there is a limit to the amount of resolution of pressure that you can apply on the tissue. As you would know, you would have done experiments in your school days. Whenever you do experiments, you have a series of inputs and then you see the series of outputs, and then you try to understand how the output is related to the input, correct? Then when you give the input, how do you give? You start from 0 or a very low value, then you will already have the highest value of input that you want to give. Then you will slowly increase the input in a finite step size. Let us say you are measuring an electric circuit and you give voltage as input, and you know that your system can take maximum 5 volt input. How do you start doing the experiment to test it? First you start off with 0 volt. You will apply 0 volt and see is there any output at the output terminals, and then you will increase by, depending on the capability of the input source, you will increase your volt and the amount of resolution required by your circuit you give in steps of very low value. Let us say you give in steps of 0.05 volt. So, you start with 0 volt, then you increase the input voltage by a step of 0.05 volt up to 5 volt. So, your first reading will be for input of 0 volt and what is the output voltage. Your next reading, your input of 0.05 volt and what is the output voltage. Then your next input will be 0.1 volt and addition of 0.05 volt, what is the output voltage. Like that you will go to 5 volt. So, how many input readings would you have? You will have 5 volt by 0.05. So, you will have 100 input lines or experimental attempts, and you will see the output voltages. On similar lines, when you want to do an experiment to do the input voltage characterization, not voltage, to do the stiffness characterization of the tissue, you should be able to apply force on your tissue from very low value to a very high value, like the breaking stress of the tissue. Till that point you should be able to apply step pressures, which is not possible with your bare hands. There is a limit to which you can control the amount of pressure that you can give. It is so you need some equipment or some system to allow you to give these micro or very small step sizes of pressure to be applied on your sample, so that you can characterize your sample very well and have a good fit mathematical model for the stiffness or elasticity of your sample. In this case, your sample is a tissue, it can be anything. So, it is in this application that a micromanipulator comes into use. Your physical system, like your body, is not able to give this finite step sizes. Just like a voltage source gives voltages in very finite steps, this manipulator can give you manipulations of micro level, either through distances movement of distance, or through an indenter with the amount of pressure that is applied on your tissues. So, this background I wanted to give you before we start off with the micromanipulator system, so that you will be able to appreciate the importance of this system. So, as I have told, these micromanipulator systems are used in a multifarious sectors. So, one is this, where you are measuring the stiffness properties of different samples. Another one is you can attach probes to your micromanipulator to characterize the electrical properties of your designed sensor. So, there is an equipment called 4-point probe, which also uses 4 micromanipulators to attach probes onto sensing pads of your sensor, sense in a voltage and sees the response current to check the resistance properties of your sensor. I will come to the details of that soon. So, now let us get started off to see the system at a broad scale, and then into the nitty-gritties of the system and what all ports, what all features are available. So, here we have the micromanipulator system. So, Okay. So, this white platform that is there is a main unit, and this black platform that is there to the right is a control unit. Okay. The control unit forms like the brain or the main heart of the manipulation system as far as controlling goes, and the manipulators themselves are these two black platforms. So, these two are the micro manipulators. This is manipulator A and this is manipulator B. These two are like hands which you can control and have micro movements. So, these two are micro manipulators. They are connected to the control unit through cables. Now, let us see. First, I would like to show you the broad aspects of the device before we go into the details of it. So, let us look at the micro manipulator in slightly more detail. So, I am just pushing the main unit towards you so that you can see it. So, this is the manipulator. Okay. So, I am just tilting it a little bit. So, if you see here, the micro manipulator will be able to move in x, y and z directions. So, if you see here, this is the y direction scale. Can you see the scale here from 0 to 25? So, that shows that the manipulator can do movement of 0 to 25 mm. Okay. This total is around 2.5 centimeters or 25 mm. So, it can travel in the y direction through 25 mm. That is the scale or range of movement of the y movement of the manipulator. Understood? Likewise, if you see the z direction, you see 0 to 25. So, again that is the same thing. So, in the z direction, the manipulator can move from base position to up to 25 mm of height. And then we have seen that this is micro manipulator. So, that means we should be able to manipulate its movement to the micro level. Shortly, when we see the control unit, we will see that this 25 mm is shown as 25,000 microns in the control unit. That means you can control up to a resolution of 1 micron in the controlling. So, you can like 25,000 micron, 24,999 micron, 24,998 micron, like that you can reduce it. So, you can adjust the movement of the y, z or x direction from 25,000 microns or 25 mm to 0 microns. We will see that clearly when we see the control unit. Now, I am introducing you to the basic aspects of the manipulator. So, you have seen the y scale, you have seen the z scale. Now, to see the x scale, I am just tilting it. So, I think you can see the x scale here below, that is also 0 to 25. So, we have 25 mm of movement in the x direction, in the y direction and in the z direction. Clear? Now, that is for the coordinate movements. Now, if you see closely, so in this manipulator we have attached some things. Let us just check the manipulator B. This both are same dimensions are there, 0 to 25, 0 to 25 and here if you see it closely, okay, and the back side it will be there 0 to 25. So, these also has 0 to 25. Now, this manipulator is like an arm. So, when you are pushing something, you need to add some stick or probe in technical terms to the arm, right. You have to connect some probe to your arm, just like your hands. You assume that these manipulators are your hands. When you are probing, before we were intending the nut with a 3D printed indenter, right. There our hands were the manipulator, but they were not capable to do micro manipulations. These are much more efficient hands, they can do micro manipulations, but we should be able to attach indenters or probes to those hands. So, this is the point where we attach probes to the manipulator. So, if you see here, if you can see an angular scale here. So, we can attach an angular scale here. Let me just tilt it. Do you see a hole here? So, you can actually attach any probe to this. So, let us say I have this tool with me, I can attach the probe like this. You can adjust the gap like this, you see, then I can insert the probe like this and then tighten it. So, I have attached a probe, so it has become like a hand, you see. Now, the hand has some probe to manipulate its target, you can see it attached here, clear. So, this angle, so now it is kept at this angle, right. Now, we can actually make this, change this angle like this to any direction we want by adjusting this screw here. If you loosen this screw here, you can rotate this part and it can tilt whichever we want. This plus part is for loosening it and then tightening it to whatever dimensions we want. Okay. So, these are the main flexibilities or the degrees of freedom in technical terms that the manipulator has. So, which all did we see? There is an x direction, there is a y direction, there is a z direction, each with a range of 0 to 25,000 microns. There is a probe holder or an indenter holder which can actually rotate through at various degrees of angles which are seen. There is a knob to adjust and attach your probe onto this holder. Now, if you see, look closely, instead of this probe holder, we have attached another interesting piece to this indenter holder or probe holder. This is because now there are several options. You see these dots here, holes, there are holes here also. You can attach your indenter to this holder itself and then the indenter can probe from here. So, this is like an extra attachment to the manipulators. So, I hope this is clear to you. So, we have two manipulators, manipulator A and manipulator B. These they form the main, what do you call, the people who do the work in this instrument, and the brain that controls the items that do the work is the control unit, which we will go into detail shoot. Now, let us see how the manipulator is connected to the main unit. For that, we need to look at the back side of the main unit. So, let me just rotate it so that you can see the back side. So, you have to be very delicate by handling this equipment. It's a very costly equipment, but they serve a lot of purpose. So, now you see that this is manipulator B and this is manipulator A. You can see motors here which control the micro manipulations of the equipment. Now, how do they communicate with the main unit? They communicate with the main unit through these connectors. I am just taking out the connectors. So, this system is completely modular. By modularity, what do you mean? By modularity, what we mean is each important component of the system we should be able to remove it and service it or look at it as an individual whole. So, the manipulator A and manipulator B come as separate entities which can be connected to the main unit through these connectors. So, I have taken out the connectors, if you see. So, this is a 25 pin connector, 24 pin connector. So, the entire communication, control data, measured data, all communications from the main unit through the control unit goes to the manipulator through this connector. This connector is eventually connected to these ports. So, if you see clearly, just look at the back side of the main unit, you see the manipulator B and manipulator A, manipulator A, manipulator B. So, manipulator A, manipulator B, these two are the two cables, they come from here and they end up in the manipulator. So, let me connect it back. Okay. So, these two form the main connections from the main unit. Then we have the power supply connector, as you can see power supply has to be connected. So, power goes to this main unit and the main unit distributes power to the manipulators as well as the control unit. To the control unit, all data comes and goes from the control unit through this command input port. If you see here, the command input port is a RJ45 connector. This RJ45 connector. So, this RJ45 connector connects to the command input port of the manipulator. So, I have connected it back. Okay. This is the command input port. So, let me just show the control unit to you now. Okay. This is the back side of the control unit. Okay. This controller is again an RJ45 connector. So, the controller's control lines go from here, and the power for the controller also comes through these RJ45 lines. So, from this wire eventually goes around and then finally ends up in the main unit. Okay. What else does the control unit have? The control unit has a configuration port where there are DIP switches. Here, can you see? So, there are switches here which you can toggle, and so they have kept it in the we have kept it in the factory default settings. So, these toggle switches can be changed to configure the ROC or the control unit, which is called ROC here, to work at specific requirements. Then we have an USB connector if you want to control the manipulator or the control unit through a system, which also we will be showing in this module or in a future module. Through this USB connector, you can actually control the ROC itself from a software and then make the manipulations to happen through the software. So, these are the only ports that are there in the manipulator, and there is a calibrate button here. Once power is turned on, if you press the calibrate, the manipulator will calibrate its movements and make sure that when we actually make a movement for 1 micron in the control unit, there is actually a movement of 1 micron on the manipulator. So, that is what you call calibration. So, that is how you do the calibration. So, these are the main ports available backside of the control unit, and those are the ports available in the main unit. So, these two are fans for cooling the main unit, because it has its own power system to take in the input voltage and then convert it into the different voltages that are required for the manipulators to function, as also the different voltages required for the ROC or the control unit to function. So, we have seen these two connectors are there. These are connected to the manipulator. We have the command input port that goes to the controller. Then we have expansion port. Right now we have not connected anything. So, let us say we want to connect extra manipulators or extra control units to this main unit. Then they have another RJ45 port here called the expansion port that can be connected through this extra system can be connected to this expansion port. Then we have, just like we saw a configuration port on the control unit, this one you have seen the configuration port, right, on the control unit. Just like this, on the main unit at the end you can see a configuration port, you can see that. So, this configuration port is there, and you can configure each line on it as per the data sheet provided, and then configure for multiple types of operation. So, these are the main functional ports or connections that are there between the main unit, the manipulators, and the control unit. So, what are the three main components of this micromanipulator system? So, this micromanipulator system, for your information only, is called, the model number is called MP385, and it is supplied by Sutter Instruments. So, Sutter Instruments is a kind of a global leader of supplier of good quality micromanipulators. So, that is why we have purchased that from them. So, this is from Sutter Instruments. So, why I am telling this is, micromanipulators made by other companies might not look the same, but their fundamental philosophy of operation will be similar. If you understand this system, you will be able to quickly understand any other different system that is made by a different company. Now, let us just see the specifications mentioned on the main unit. So, if you can see, the main unit needs an input power of 100 to 240 volt, 50 or 60 hertz. So, in India our input voltage is 220 volt AC at 50 hertz. So, this unit can take in that power. So, it just takes in that power from this power cord and makes all other DC voltages required for every other component to function. That is the reason why, one of the reasons why this unit is the bulkiest, because it has lot of power modules to cater to different power requirements of both the control unit and the manipulators. And then it is telling T2 amps, 250 volt, 170 watts maximum. That means it uses maximum of 170 watts when it is used in full 100% utilization. So, these are the main, so you can see the company name written, that is not important here. So, these are the main ports, as I have told, and connections. You should, before you start understanding any equipment, you should know how the different parts of the equipment talk to each other before actually going into how the equipment works. Because if you directly try to understand how the equipment works, and if somehow things do not work as you expect them to be, you should be in a position to debug on your own what would have gone wrong or where it would have gone wrong. For that, it is very important for you to have a holistic view of the connections in your equipment, and you should not always depend on the service engineer from the company to do minor changes for you. So, most of the things that might not work, you should be able to debug at your lab itself. For that, it is very important that you understand what are the connections, basic things, so that because if you do that, if you are in a position to debug or fix minor things, your work will also progress faster. Otherwise, the people who come to service, they take time. We have to raise a ticket, we have to ask for help, there is an online set procedure, then they will take it, and most of these equipments are imported. They come from either USA or European countries. So, you have to wait for their response, and they have to come, and finally, when they come, you will realize that they will fix it in 1 minute, under 1 minute, and also you being engineers and researchers in the field which uses these equipment, you should be as good as or even better than the people who come to service. Unless there is something that you need to change and you are scared that it might affect the warranty or the guarantee of the equipment, then you should not touch it. Other than that, if you are confident that you will be able to make these changes and fix the small problem that has occurred, you should go ahead and do it. For you to go ahead and do that, you should understand, you should be able to know what are the different connections, how is each module communicating with another module, and what might go wrong where. These things, if you know, you will be able to debug it properly. So, now we have seen basic components. Now, we have to power on and see how these things actually work. So, let me reset it back to the home positions. So, now we have kept the system, the equipment back to its home position. We had shifted it a bit to show you the ports available at the back side of each of the components. Now, we have kept the micromanipulators, the main unit is there, the control unit is here. Now, another way where another arrangement of how it will be arranged is that there will be a microscope at the bottom. Okay, the microscope's eyepiece will be here. So, we will observe, this is the work area, and manipulators, indenters or probes will be connected like this, as I had shown you how probes will be connected. Probes will be connected like this, and this will be your work area. For you to have better visibility, the control unit would be kept here and the microscope would be here, and you will see your work area through the microscope and then manipulate it from here. So, because that would be a very complex arrangement for you to understand, that is how exactly we would be using it, but then for you to understand this equipment alone, we have kept it in a simpler arrangement. Please be sure about that. So, manipulators are kept on top of the main unit right now, for that it is clearly visible to you. When we move this, you should be able to see the movement, that is why it is kept at this level. So, now we have a power on off switch. Finally, the moment we are waiting for it to come, we are going to power it on and see. So, once power comes, you see the green light coming here, and then as I have told, the power to the control unit also comes through the main unit. So, the control unit also has powered up, and you can see the display here. Is the display clearly visible to you? Yes, you can see the, so if you see here, there are in the display there are mainly 3 sections. One is drive. What is the drive that you are using? So, you have manipulator A and manipulator B, right. So, it is showing drive A. So, manipulator A is being driven. Then you have mode. So, you can go up there, it is showing that it is mode 0. Mode 0. Mode 0 is visible, drive A is visible, then you can see Z, X and Y values. So, Z, X and Y can go from 0 to 25,000. So, Z, X and Y can go from 0 to 25,000. So, I am just making it back to 0. Okay. Now, Z, X and Y are at 0. Okay. So, one is drive, what is the manipulator that you are driving, and then one is mode and one is the Z, X and Y values. Okay. Now, it is very clearly visible to you, there are 3 knobs available here. One is for X manipulations, one is for Y. So, the top one I am changing it. When I change it, you can see the Z values changing, correct. So, this is the Z manipulator. Okay. Now, this is the Y manipulator. When I am changing the Y, you can see the Y values changing. This is the X manipulator. When I change X, you can see the X values changing. Clear? So, then drive. So, let us see the knobs or buttons that are available on the control unit. Okay. So, we have manipulator selection here. So, there are 1, 2, 3, 4 is written. That means you can connect up to 4 manipulators to this control unit. You can even have more than 4 manipulators connected to the control unit, but you need to add another controller through the expansion port which we saw earlier. So, that expansion port needs to be connected. So, this manipulator, so if we press it, the control will go to the second manipulator. See, now it has gone to second manipulator. As it is well aware to you, we have connected only 2 manipulators to this control unit, correct. So, manipulator 1 and manipulator 2 only make sense, the other 2 are not available. So, that is why even if you change the mode, it will only switch between one manipulator and the second manipulator. It does not go to the third and fourth because the system has not detected extra manipulators connected to it. So, that much intelligence is there in the control unit. So, right now let us keep it back to controller 1. So, when you connect to 1, the manipulator will be able to control manipulator A. Okay. Then there is normal or diagnostic test. So, if you click that, it will do a basic calibration test of the manipulator. So, that is what is happening. So, that I have switched it off. Then there are 3 things. There is home, you can see home at the bottom, then there is stop and set, then there is work position. Okay. So, let us say we have started manipulating the manipulator by changing the knobs and you arrived at a position. Let us say X is 15,000, Y is 10,000 and Z is 20,000 in microns. As you must remember, the X, Y and Z directions can navigate from 0 microns up to 25,000 microns or 25 mm. And you have reached at these values, X is 15,000, Y is 10,000 and Z is 20,000. You at this value you are able to indent your sample properly, and then suddenly you got some other work and you had to rush out, and then again for you to search and seek out this value, this place, it is difficult. So, you can always save your work position here. This is the work position. So, if you save the work position, if you get back, if you just click the work position, the manipulator will go back to those X, Y and Z coordinates and you can start your work immediately instead of again seeking out the sample where it is under the microscope. To set that work position, we use this stop set button. Okay. Now, there is one more knob available here called mode. You can see here next to the manipulator. So, this is mode. Okay. If you change the mode is basically to give you control of how fast the X, Y and Z values change when you rotate the manipulator knobs. Understood? What does the mode do? There are 10 modes from mode 0 to mode 9. As you increase your mode, it gives you more control of how your X, Y and Z values change as you change your manipulator knobs. Let us say we are in mode 0, correct? You can see it in the display, we are in mode 0. Okay? Now, look at my hand. My hand is on Z manipulator. I am changing it very less. See, you can hardly feel my hand movement, but then the Z values are changing quite fast, 73, 78, 84, 85, correct? Correct? Now I am changing the mode. I am increasing it to, let us say, mode 5 or mode 6. Now it is in mode 6. Is it clear to you? Mode 6 is written. Now let me change it. See, now I am changing this much. Okay, still Z value has not changed. Now only it has changed. So again you are changing, and now only it has changed. Now you are rotating. Now only it has changed. Let us say we increase it to mode 9, which is the most finest mode. I am in mode 9 now. Here, let us say the value is 156, right? Z value. I am changing the manipulator. See, this much movement I am doing on the manipulator. Still the Z value has not changed. I am changing. I completed almost 3/4 of the circular movement, then only it has changed. So this gives you more control about your X and Y, X, Y, Z motions. So this mode selection depends on the kind of sample you are testing. So if your sample is quite destructive, and if you put so much extra pressure on your sample, in case if it gets affected, then you should be working at very high mode, so that you are making very fine changes in your manipulator's movement. For that you will have to use the mode 9. If it for general applications, you can work with mode 1. If you want to quickly characterize your sensor, you can do this. Then see, I am back to mode 0, and your Z value is changing very fast, and in one circle itself the Z value will cover almost 1000 microns of movement. Okay. Now it is very clear to you now what are the control knobs available in the control unit. You have the X knob, Y knob, Z knob. You have the manipulator selection points to select between manipulator A and manipulator B. See, when I am changing the manipulator selection, it is changing to drive B or drive A. So you can select the manipulator A or manipulator B, correct? And then you can do the mode selection also. Okay. Now let us see the fun part. So let us look at the manipulators now. Okay. Now manipulators are in view. So as I had told, this is manipulator A, this is manipulator B. Now you need not see the control unit. So I have kept you just focus on the manipulators. You are seeing the manipulators in the control unit. As you remember, I had kept it in manipulator A control. Now I am changing the Z manipulation. Okay. Now you closely observe the manipulator A. I am changing the Z manipulator. So do you see the manipulator going down? In the Z direction? So I increased it to 25,000. So it has gone down fully up to 25,000. Fully gone down. Now let me go back to 0. So you can see the manipulator going up. So this way you are able to manipulate it in the Z direction, correct? I am moving it up and down now. Now let's try to move it in the X direction. See, you can see the mark also below. We have moved it full 25 mm or 25,000 microns, correct? Now let me go back to 0 position. You can see it moving in the X direction very clearly, correct? So let me keep it somewhere in the middle, because I wanted to show you the home knob. Now Z also I will keep somewhere in the middle. Okay. Now Y direction, let me just manipulate it Y. You can see it going back. Clearly you can see it going back. So I am manipulating it in the Y direction by changing the control unit. Okay. Now it is in some x value, some y value and some z value, correct. You might have remembered the home button in the control unit, right. Now if I am going to press the home button, once I press the home button, you will see the manipulator automatically adjusting its x, z and y to the home or the 0 value. Okay. Let me press it. So you saw it now, x, y and z went back to its home values. Let me just show it to you again. So I am again fixing z to somewhere in middle, pushing it down. X I am pushing it to somewhere in middle. Okay. Y also I am pushing to somewhere in middle. Clear? Okay. Now I want to start fresh. I will press the home button. When I press the home button, x will go to 0 position, then z will go to 0 position, then y will go to 0 position. Clear? So instead of you going to do that, the system provides single button to do this. Now as I had told you, there is also the work position. So I have saved a work position for manipulator A. Now if I press work position, it will go to that work position. So I pressed work position, so it is going there. So the work position is z value of 12,321. If you see here, let us see in the control unit. Okay. In the control unit, the work position is z is equal to 12,321, x equal to 12,484 and y equal to 12,471. I slowly adjusted it. So let me go back to the work position. Okay, 12,315. Clear? So this is the work position. Now let us try to manipulate manipulator B. I am changing it now. Look at the control unit. I am changing the manipulator to manipulator B. Clear? Now let us look at manipulator B. Okay, this is manipulator B. Okay, now manipulator B is in your viewpoint. Let me just change the z value of manipulator B. You can see it going down. Clearly? Yes. Then let us change x. Clear? Let us change y. Clear? Now let us go to home position, just like manipulator A. You go to home position, x, y and z will change. Clear? And you can go to a work position. So it is going to a work position also. It's clear to you? So this is how the manipulations are done. The x direction, the y direction, the z direction. What does the home button do? It will go to the home configuration or 0 configuration, 0 position. And the work position is something that you can save and then go back to every time you reuse the equipment. Now let us look at one more thing. We have seen the micromanipulators. So these are the hands of the equipment, but we have not given any tool to the hand, right? So as I had shown you, let us look at manipulator A now. So we had seen manipulator A. We have seen that there is a indenter holder for the manipulator, correct? And we have attached this indenter holder here, which has lot of holes here, which will allow you to attach several indenters to this port. Okay. So we have 3D printed, using 3D printing technology, we have 3D printed quite a big macro scale indenter, so that it is very visible to you. So this is the attaching part of the indenter and this is the tip of the indenter. With this tip you can actually interact with a sample. So we can attach this to this port of the sample holder. So let us say, so it is there like this, we can attach it. So we can attach it with screws. Okay, I am attaching it with screws. Clear? So I have to put a nut. So let us put a nut. So, one nut is put, and then tighten it from behind. Okay. Okay, we have to put the other nut also. Okay, so it's okay if you don't put the nut, it's reasonably tight now. Ideally, we should be putting the second nut also and tightening it, but this is how it will work. Just pause. I will put it. So let's put the second nut also. So this way the equipment gives you a lot of flexibility. So because of this stand is there, so this connector is connected to that sample holder or the indenter probe holder. You can 3D print or you can fabricate any kind of micro needle or whatever you want, and then connect it to your micro manipulator and indent it. So there is a lot of customization probabilities, possibilities that are there available to you. It does not mean that they have given you this equipment and you have to use these needles or these probes only to interact with your sample. It can be anything. So these are exactly like your fingers. You can hold anything you want with your fingers, correct? So they are like that. Okay. So we have connected our 3D printed indenter. Clear? We have connected 3D printed indenter to this manipulator. So for fun's sake, for your own interest, let's just manipulate it in the Z direction. Okay. So now with the indenter, your manipulator will go down, correct? And it will go up also. Let us say we have to interact with some sample. Let us just keep some sample at the bottom. Okay. Okay. So let us say I am having this wafer carrier. Okay. This is a wafer carrier, and this is your let us say your sample is on top of this. So if I am manipulating it, I am bringing it down. Okay. So when it comes down, it will touch it, see. So when it touches it, it will apply pressure. You won't be able to see it because it is already interacted with the wafer sample. Okay. So it has gone up, then we are bringing it down, and then it is interacting. Clear? So this way you can increase the pressure applied. Like this. So this is how you usually test with the micromanipulator. Instead of this we will have a sensor and sample on top. With that experiment also we will be doing soon in another module. So I think this would have given you a very good introduction to how the micromanipulator system works, what are its uses, how it is used, where it is used, what are the different components, micromanipulators, what are indenters, what are the probes, how can the probes be connected, how can you have angular arrangement for your probes, what is the main unit, what is the power requirement, how does the main unit provide supply to the other manipulators and the control unit, how the manipulators are like your hands, and how the probes are like your the tools that you hold in your hands. Hope that is understood to you. Then you saw the control unit, which forms the brain or the controlling CPU of your manipulator. What are the different knobs available in the control unit, the X manipulator, the Y manipulator and the Z manipulator. What are the different modes, why there are different modes, what is the use case of the different modes, how do you change from one manipulator to the other, what is home position, what is work position, what is diagnostics, what is calibration, and how do you set your work positions. So I hope this has given you a wholesome understanding of how manipulators work. In another module we will also see a short experiment where we will force indent a pressure sensor and see how it responds. So see you then.